0-1 delivery to him and a towering shot way back.
There's always a tiny gap between what happens in the world and what we see. The data arrives, but always one beat behind reality. If you're running separate tasks, you could have torn reads, inconsistent data, or moments that never actually happened. So today I'll walk you through 3 ways to share data: the broken way, the slow way, and the fast, clean way using my new library, SnapshotBus. Welcome to more Little Man Builds. To explain what's going on in the code, I want to simplify things. Think of the umpire as the writer, the source of truth. He's the one announcing what just happened. And think of the scoreboard operator as the reader, the person trying to display that truth to the crowd. And just to be clear, I'm not simulating the Major League Baseball here. Come on, I'm Australian and should have just stuck with cricket. These are just simple fields which change over time so that we can show how things go wrong when multiple values aren't updated together. So let's start our first sketch in serial plotter and we get rid of age in milliseconds for now. So on one core we've got the umpire, the writer, and on the other we've got the scoreboard operator, the reader, trying to display it. We've got our 3 fields which are changing: score, inning, and call. The writer updates these fields one after the other, not all at once. Meanwhile, the reader just grabs whatever is in memory at that exact instant. The red errors per second is when the consistency check fails. Each spike is the system catching a frame that's logically impossible. The numbers just don't stack up. The green line, latency microseconds, stays nice and low as the reader never waits. It just copies the struct and carries on. If we add back in the age in milliseconds, this is how the old data appears to be when the reader plots it. It's sawtooths all over the place because sometimes the reader is using a fresh timestamp with stale fields and sometimes stale timestamps with freshly updated fields. This is what unprotected shared memory looks like in practice. Fast, fresh, and fundamentally wrong. So how do we fix this? Well, the simplest way is to force the scoreboard operator and the umpire to take turns, and we'll do this by adding a mutex. A mutex is a little lock that forces the writer and reader to take turns. The mutex ensures that only one task can touch the shared frame at any one point in time. So we've loaded up our second sketch with the mutex, and the effect is immediate. The errors per second counter drops to 0 because every snapshot is now internally consistent. There's no half updates, no impossible combinations, just a complete valid data frame. But there's something subtle that's worth pointing out. Score and call match as they're the same value when the reader takes its copy. That's why EPS stays flat at 0. But then, why do the lines drift apart just a little? It's not an error, it's timing. Here's what's really happening. Score was produced by the writer using its own clock time during the last publish. Call is computed fresh by the reader using its own clock time at the exact moment the frame is plotted. Both clocks advance together, but they are out of phase by a few milliseconds. So score reflects the moment the writer updated, and call reflects the moment it was read. Same value, same logic, just slightly different moments. And that's why the lines appear offset sometimes. The green line is the latency of each read. It's stable and predictable, but much higher. With the mutex, the reader sometimes has to wait its turn. It's kind of polite, or it stands in line. So latency goes up just a bit, but at least it's not chaotic anymore. When we add back in the age milliseconds, every time the scoreboard operator finally gets the lock, the data is already a few milliseconds old. Correct data, but delayed. So now we've seen both extremes. The race condition was fast but wrong, and the mutex correct but slow. So the natural question is, can we get correctness without waiting? And that's where SnapshotBus comes in. So we've loaded up our last sketch and let's give it a crack. The SnapshotBus library solves the problem by changing how we update the data. Instead of writing one field at a time, the writer prepares a complete copy of the frame and publishes it in one atomic step. Look at the difference. Score and call always sit directly on top of each other. They're reading the same moment in time. EPS stays at 0 permanently, no torn updates. Latency nearly disappears because the reader never waits. There's no lock, just a clean snapshot ready whenever you need it. Age stays low and stable. The only delay now is the natural gap between publish and read. No contention, not waiting. By the way, if you're enjoying this content, smash the like button or please consider subscribing. It really helps me out with the algorithm and I'd love for you to join our community. Apologies, managed to get a little bit sick, but maybe I have a better studio voice now. Let's open an example sketch using our SnapshotBus, and we'll just choose the first one, basic polling. So what we're going to do with this sketch is publish a tiny struct from one task and read it in another. We've simply defined a button pin, and I just want to point out that I did make a mistake in the comments. This should say pin number 7. So this is a pretty simple sketch. We've included our SnapshotBus library, and we've also defined a snapshot payload, which has a struct input state. So this is whether a button is pressed or not, and the timestamp for when that event actually happened. The most important part is this global snapshot channel, which is pretty much just maintaining the latest state, and think of it like a little mailbox that always keeps the most recent letter. We've then got 2 tasks. We've got a publisher task, we've got a consumer task, and each of these are running on a different core. So we've got publisher running on core number 0, and we've got consumer running on core number 1. But the important part is that the 2 tasks don't know or really care about each other's timing. The producer can run faster, the consumer can lag behind, but nothing will ever block, stall, or corrupt the data. And that's really the power of the snapshot model. You're not asking what just happened, you're asking what is true right now. It's a small sketch, but it's a pretty big architectural win, and I hope it makes sense to everyone. So now let's test it out. Let's bring in our serial monitor. I've sent it across to the ESP32 already, so the code's already running. Let's bring in the camera. So now when I press the button, we get the press event, and when it's released again, the release event, or it goes back to the status quo. So I'm not trying to reinvent the wheel here, but I am trying to ensure that with this library, we get really fast, efficient, and correct data transfer, because this will become increasingly important with our car project. And honestly, after implementing SnapshotBus, I've stopped fighting with locks altogether. Clean frames, it scales beautifully, there's minimal latency, and it just works. So for system with multiple tasks, threads, or cores, ask yourself, do you want correct, do you want fast, or do you want both? So now let's start using SnapshotBus within our car project. We had already cheekily snuck it into the project in one of the last videos, but this particular video we're going to focus on the library itself. We have added some extra functionality, so just make sure you've updated everything within the library manager. So the next file we'll look at is our input types. So now we're not inputting the snapshot model, now we're just generically calling it an input model. Because of this, we also then need to update here. And that should be everything for this particular file. So now let's create a new file called RCBus. So what do we need? We want to create a struct. We'll call this RC snapshot. So the next thing we want to do is read a single value from our RC snapshot. Let's also use a type alias to save on typing. And lastly, we need a single shared RCBus instance. Save that. So that should be everything that we need in that file. So we can close RCBus. Now, last time we had what we called an RC listener because we were listening to all the signals from the remote control. Realistically, we're actually publishing the signals from the remote control to whichever task needs to look at that particular data. So I want to just rename things for consistency. Let's update our include files. I've created another file which helps build the RTOS tasks rather than having to actually do it ourselves. And this will become a little bit more clear later. So we can say rcbus.h. So we still have our RC publisher, but we do need to update this. So we're going to add in 2 more variables. So effectively what we're saying with our epsilon is that if there's a movement on our remote control that's greater than a certain variable, then publish this change. And for the purposes of today, if we set it to 0, then we are always publishing on any type of change. And of course, we've got a min interval in microseconds to publish at least this many times. So we should update our method. Still takes our standard period. epsilon is 0, minimum interval is also 0. We still need to configure our RC link, but there's no need to do internal calls for any FreeRTOS tasks. So we no longer need the task trampoline, so we can get rid of this. Again, there's no need for an internal run now. So we still have aliases. We still have state, or we could call these internal state variables. So we have our transport, our period, but now we also need those two additional variables that we added up here. So our epsilon, which is effectively what we could call a change gate. If there's a change above the delta, then publish. So the important part now is that we need to have a reader that adapts the RC link to SnapshotBus. Well, actually, sorry, to SnapshotRTOS. By the way, if you're enjoying this content, smash the like button or please consider subscribing. It really helps me out with the algorithm and I'd love for you to join our community. If either asserts failsafe, then it's not okay. So we also need to update our constructor. So the reason this is because I forgot to update here. So last time we had our configuration variables, we had our switches. We no longer need our main run loop because we're not creating a task trampoline at all. We're letting the SnapshotRTOS publisher do it all for us. I now want to introduce some failsafe policies. So this means that if for whatever reason the remote was to disconnect and I could no longer receive the signals, I can configure our variables to whatever I want. And pretty much we can do this for all the other variables. So I'm just going to do a copy and paste. But for this particular channel on my remote control, this is where I override all the car settings. And so for this one, I want to make sure the value is actually selected to 1. The next thing we want to do is to make sure the receiver has a failsafe signature for testing. So I can configure whatever this is on the remote control and mirror this in code.
So just quickly want to talk about what I mean by failsafe. So in an RC system, failsafe means that if a receiver stops getting valid signals from the remote control because of interference, loss of range, or a dead battery, the system immediately switches to a predefined safe state. Now, what is that safe state? So in the FlySki RC, we can press and hold this button here, and this also works as the enter button. And what we're going to do is go down to the receiver setup, and then we're going to go to failsafe. So if we quickly go over the channels again, channel 1 is left and right, channel 2 is up and down, channel 3 on this slide is up and down, and channel 4 is left and right. So I don't think we'll be in this calibration very often driving the car. So as you can see, the failsafe values for channel 1 and channel 2 are 100, and channel 3 and channel 4 are 100 and negative 100. And this is the data signal that automatically gets sent when any failsafe is triggered.
So in this case, when I set my steering to positive 100, the direction to positive 100, the speed to 100, and the indicators to negative 100, then this will trigger our failsafe signature and put us into failsafe mode. So now, after that, we want to apply all these and then apply the configuration still. Next, we need an adapter. So we're going to say RC publisher. Now, let's add in here a short alias for the snapshot RTOS helpers. So let's just comment this. We've all seen this before, even though it doesn't look like it. The polling period in milliseconds. So we've now fixed our RC publisher, so we can close this. We also need to run it somewhere. So for today, we will use the state manager task, even though in the future this will change. In this case, we do need our task trampoline. And under here, and the reason that won't work, got our I button handler. We need to add these variables here. So there's our state manager .h updated. Let's fix the .cpp. Let's create a demo section of code just so we can read everything for today. So this is to remember the current state. And then last but not least, we still need to update our main.cpp. And because we're not running a task trampoline, we don't need to worry about the separate tasks and all the other elements that go with that. So that should be everything. Let's see if this one compiles. No, what have we done wrong? Has no member named update. So I think I've forgotten something here. We didn't have any method to update the RC links, frame, or state. Try again. So let's send it over to the ESP32 and give it a test. When it initially loads, nothing will be running because the remote control is not on. So let's bring in the camera and now let's turn the remote control on. And so now that you can see that the speed is 0, and as I increase the remote control speed, I can adjust it. Should be 0. There we are. So as we discussed earlier, I can trigger failsafe by putting the car into this configuration. So it immediately stops and back again to adjust and just to prove it one more time. Or it might also be that there's a loss of power. So if the remote control is turned off, we also see that the failsafe immediately triggers. So it works really well. Today we saw 3 completely different worlds. But when you fix how you share data, your entire system feels instant, and for us, this is key for responsive car behavior. All the demos from today, the baseball sketches, and my entire Ride on Car project is available on GitHub, link in the description. Please also consider subscribing and smash that like button. See you in the next one.